Q symmetric has a negative property. So a square matrix is said over a ring is said to be symmetric if A transpose equals A, skew symmetric if A transpose equals minus A, orthogonal if A transpose equals A inverse. Let F be a field and be a vector space over a mapping. F is called a bilinear form if the three properties below is observed or hold. So show that the sum of any two bilinear form is also a bilinear form. So we let F and G be two bilinear form of V, and we pick alpha U1 plus beta U2 comma V. So similarly for GV cross V, then the sum of two bilinear form F plus G should obey the two properties, and at the end of the day we arrived at the sum is linear in the first variable. So we need to show that it is linear in the second variable. Meanwhile, it is linear in the first variable. Why? Because we use the first properties of both F and G. So to show for the second property, we need to prove that we need to use the second properties too to show that it is linear in the second variable. And at the end of the day, it is proved that it is also linear in the second variable. So this means that the sum of two bilinear form is also what? A bilinear form. So we have U to be x1 to 3, V to be y1 to 3. Then we have F of U comma V. So we have to express this in matrix form. So we write out the coefficient of Cx y1. So as represented Cx1 y2 Cx1 y3. So we write their respective coefficient from the question, and we have our matrix. So we have a mapping R3 to R2 as a projection, and we are asked to find the matrix of A with respect to the standard basis of R squared and R3. The standard basis of R2, that's 1, 0. For R3, that's 1, 0, 0, 0, 1, 0, and 0, 0, 1. Those are the standard basis for R3. And when the values of x and y are solved simultaneously, we have x to be 1, y to be 0, x to be 0. You can see clearly the values in form of red are written diagonally in the matrix form. So similarly, we have the R2 matrix to be 4, 3, 3, 2, and R3 basis to be 1, 0, minus 1, 1, 1, 1 respectively. So we do similar thing. So if we open the bracket, it will be 4x plus 3x plus 3y 2y, and when we equate it to 1, minus 1, 1 is representing the values for x and y is representing the value for minus 1. When we solve it simultaneously, we have x to be minus 5 and y to be 7. So similarly for the other bases that we have. So we have our final answers to be minus 5, 7, minus 2, 3, and 1, 1. So we have B to be represented below. When is an R module said to be finitely generated? So we have the readings there, which is clearly stated. Every finitely generated R module is homomorphic image of O. This is, we need to prove for well-definedness. So for well-definedness, since it is a finitely generated module, we recall that f of a is sum of a1 x1, and from the above we already have the definition of a finitely generated module. So when we take the sum, we pick f of a, f of b, where a and b up to n, they are in f. So well-definedness is proved. Also, we prove for the scalar multiplication. Now let's keep B a quadratic form associated with a symmetric bilinear form. We are asked to prove that. So knowing fully well that f q u plus v will give us f of u plus v, v u plus v, and qu will give us f u, u, qv will give us f v, v. When we cancel out the necessary values, we arrive at f of u, v. And note that for symmetricity, f of u, v, same thing as v, u. So similarly for 1 over 4 qu plus v minus qu minus v. So it is stated. You can as well pause the video and go through the examples vividly. So we have another example here. V equals to R cube be a vector space over a ring R, and the bases are given respectively. We have to show that V equals to the sum of Rxi ranging from I to 3. To show that V is an R module, we need to show for M1 to Mn. So a finite collection of R module, then we set the Cartesian product M1 times N to Mn as the R module operation. So M1 representing 100, M2 110, N3 111. So adding the 3 together, we arrive at the sum of I1 to 3. So let R be a ring and S denotes set of all sequences. So defining both A and B, we need to show that S is a left R module. So we recall all the antecedents for modules and we apply them respectively, and at the end of the day we show that it is an R module. So let M equals to M1, the direct sum of M2, then M1, M2 are submodules of M. So from first isomorphism theorem, M1 over M1 intersection M2 is isomorphic to M1 plus M2 over M2, and this is generated by 0 and is isomorphic to M over M2. So M1 is isomorphic to M over M2. So that is proof. So solution to the test questions, we have to define module and module homomorphism. So let file be M to N. So show that the kernel of file is a submodule of M and the image of file is also a submodule of N. So we have the respective definitions below. So we have the respective definitions below. So it is easily proved and well understood. So we can as well go through them. So let M be an R module, show that the union of Mi is a submodule of M. The proof is given, well stated. So we have torsion element, torsion module. If all the elements of M are torsion elements, and when it is replaced with an integral domain, we have our proof stated below. So we have modular law for modules. Then we have to prove the fundamental theorem of ring homomorphism. We have when is a module M said to be cyclic. So this is all for this video. You can as well pause the video and check through the writings. Thank you.